Okay? So it may not be 8% annual growth. It can be actually 80% annual growth, okay, for the next 10 years. So how do you support all these users with all these base stations? Here is one architecture that's been proposed, okay, by many network vendors, and the commercial name they attach to it is Cloud Radio Access Network. So here is how it goes. Okay, so we have multiple base stations, right? And we somehow want to put them together to form a nice network. Now the trouble here is if you bring down your radio close to end users, then your direct communication is good, but at the same time you are increasing your interference. So here the red signal is what you want to get, but it causes the blue ones, which is unnecessary interference. The way of handling this interference is you want to have some central point which controls all different base stations and try to do some coordinated communication among all these base stations altogether. It can happen for uplink communication, so everybody is talking to its closest base stations as relays, and then they are all propagated, the signals are propagated at the central node, who can finally decode and send it further to other networks. And we can also do the same thing for downlink. So this type of cooperative communication can be a nice tool to handle hugely increased interference in the network. So what I'm going to do for today's tutorial is, for this type of relay networks, what can it say from information theoretic point of view? Okay, so for example, what is the limit of the amount of reliable communication we can achieve for this type of relay network, right? And what are the coding schemes that achieve that limit? So these are information flow questions, network information flow questions we can study for relay networks. And this is a very well-studied area in a sense. I mean, over the past few decades, there has been thousands and tens of thousands of papers published on this topic. Okay? And naturally, what I can deliver today is a very narrow and very personally biased view on the topic. Okay? And for example, I mean, here are people in the audience who know way more than I do, including Gerhard Kramer. So it's some snapshot of what we have been discovered on this type of problem. So here is the organization of the rest of the tutorial. The first, before we go to the relay and talk about many nodes, I'm going to first study the single hop communication as a background, right? And our first stop is multiple access channel, which is many to one single hop communication. So there are many senders talking to a single destination node. And we also studied dual problem, which is one-to-many broadcast communication. And we'll go over the basic coding techniques for these two scenarios. Then we'll go to a very simple cooperative communication model, which is called the relay channel. So there, a single sender is communicating to single destination with the help of relay. And there have been many coding schemes proposed for this relay channel. And we are going to go over two canonical ones, called partial decode forward and compress forward. And once we master these simple coding techniques, we'll move on, finally, to the relay network. So for the multiple access relay network, where there are many senders communicating to a single destination using relays, we are going to study a coding scheme called noise network coding. And for its dual problem, where a single sender is communicating to multiple destinations through relays, we are going to look at distributed decode forward coding scheme. And for most of these talks, I'll not try to prove any theorems. All these results are just given as a pointer so that you can read further and try to apply to your other research problems. Once we go over these coding schemes, we'll revisit the limit, the upper bound on the network capacity. So we'll briefly review the Cossette bound. okay, which is very widely used capacity bound for general networks. And then we'll extend this to something called directed cut step bound, which I'd like to call also as cut left bound. Okay, and you'll see the reason later. So for these bounds, we typically upper bound the capacity using something we can easily compute, relatively easily compute, which does involve only a few channel variables and their mutual information. Okay, so are we ready to start? Do you have any questions? So we'll first look at multiple access channel. And here is a simplest version of multiple access channel with two senders, each having independent messages M1 and M2. And they would like to send these messages to a common destination node. Okay? And the destination node would like to recover both messages reliably. And we'd like to perform this communication over so-called multiple access channel with two inputs, X1 and X2, and common output, single output, Y. So by encoding message M1 in a code word X1, 1 up to X1n, the n sequence of X1 symbols, and by encoding message M2 into X2 code words, and communicating over noisy medium, and based on this noise observation, the receiver would like to recover the messages. So this is so-called multiple access communication system. We formally define how different nodes work by this code. Okay, so the rate of communication here is R1 and R2 because we are sending 1 of 2 to the n R1 messages and 1 of 2 to the n R2 messages by using the channel n times. Okay, so the rate of communication is log of the number of messages divided by the number of transmissions. So log of 2 to the n R1 divided by n, which is R1. So that is a communication rate for sender 1. And similarly, R2 is communication rate for sender 2. So these two encoder boxes, which are separated at different senders, is encoding their own respective messages into their own code words, right? And decoder is simply trying to find the estimates of messages based on its noise observation. We assume usually that the messages are uniformly distributed and independent of each other. And once you define your code, the performance of your code and communication system is measured by average probability beta, which is simply the probability that the intended messages are different from the decoded messages. And there is a nice trade-off between the rates for user 1, sender 1, and sender 2. Because when sender 2 is transmitting at high rate, probably sender 1 should not send anything, and vice versa. So there is a natural trade-off between different senders communicating to the common receiver. You can think of it as a press conference where there is, say, president or somebody, and there are many reporters, and if they are asking multiple questions at the same time, okay, if they are all talking at the same time, probably the president will not be able to hear anything. So there should be some trade-off in the amount of their communication. So this trade-off between different users' rates is captured by the notion of achievability. So we say the rate pair, R1 and R2, is achievable if there exists a sequence of codes such that the probability beta of their communication defined this way is 0 as we increase the block size. So this is Shannon's asymptotic approach to communication. So he looked at some threshold, or in this case, the threshold trade-off between different rates when you can have arbitrarily long communication. And we define the optimal trade-off by capacity region, which is formally defined as the closure of the set of achievable rate pairs, R1 and R2. Okay, so any rate pair inside the capacity region, we can find good codes for some large block length n that gives us arbitrary small probability beta. And if you go outside the capacity region, then there is no coding scheme whatsoever can give you reliable communication. And often we have a stronger result showing that if you actually go outside the capacity region, the probability of error is not only not going to 0, but it usually goes up to 1. So it's a really sharp threshold. For multiple access channel, the problem is completely solved. And let me go over a typical way information theorists would like to characterize and find the capacity region. So we use so-called random coding technique. So we fix some distribution px1 and px2, and we randomly generate code books, the set of code words according to that distribution. Okay, so for M1, for each M1, we would like to generate x1n sequence, IID according to px1 distribution, right? And we do the same thing for x2 code words. Okay, so there are 2 to the nr2 code words we need for sender 2, and again, we generate them IID according to our fixed distribution px2. So that forms a code book, right? And this type of random code book generation makes the analysis much, much easier because it's very difficult to construct the optimal code. So here, in a sense, we are using the probabilistic method to just look at the ensemble of code books and show that their average performance is good enough. Then that proves that there exists at least one good code book that achieves the same performance. It's similar to this idea. If the class GPA is 4.0, then that means there exists at least one student whose GPA is equal to or above 4.0. Okay? So that is the general idea of Shannon's random coding. For the decoding, whenever you fix your code book and assume all the messages are uniformly distributed, then what is the optimal decoding? It is maximum likelihood decoding, right? You simply find the code word that has the maximum likelihood. Maximum P of Y, you receive the output given M1 and M2. So that is the optimal decoding. And optimal decoding is often difficult to analyze. So we typically use something called joint typicality decoding. So we define typicality as the sequences have the type, the empirical frequency close to the true probability. So at the receiver, we find the unique message pair M1 hat and M2 hat such that the X1 code word corresponding to your M1 hat and X2 code word corresponding to M2 hat and the received output are jointly typical. Again, meaning that their joint empirical frequency is close to the true probability distribution, where the probability distribution of X1 and X2 are coming from the same distribution we generated our code book, and conditional probability of Y given X1 and X2 is given by the channel probability. Okay, and as we all know, or most of us know, the performance of this coding scheme is characterized by the ray pair R1 and R2 that can be communicated reliably under given Px1 and Px2 and the given channel. So using the standard analysis in information theory, it can be shown that whenever R1 and R2 are inside this pentagonal region, then this random coding scheme as well as the joint typicality decoding can achieve any ray pair inside here reliably. Okay?
So I have a question.
Yes.
Why is it the pentagon? Why isn't it a round shape?
Oh, for fixed
Yeah, but
distribution.
Still, why? I mean, if I was looking at this, I would say, why are there 3 straight lines?
Okay, so that requires a little more work, okay? And for those of you who haven't seen multiple access channel or even point-to-point random coding idea, it typically goes like this, okay? So when you generate your input code word X and output Y independently, okay? And there are many, many input code words. What is the probability that the wrong input code word can confuse your output as jointly typical? Okay, so in other words, when you have many inputs, and some of them may actually look as if it is a true input, even though it was generated independently. Okay? And there is a very sharp threshold coming at mutual information. Okay? So suppose this is your space of code words. And this is the output you received. Okay? And assume that all these code words are generated independently. Okay? And based on your output, you look at all the inputs that are jointly typical with this output. What is the threshold in the number of code words here so that randomly generated code words fall into this joint typicality ball? And what is the threshold for which it actually, there is no code word that fall into this joint typicality ball? And turns out the answer is mutual information. Okay, so as long as the number of code words is less than the mutual information between input and output, then with very high probability, none of the code words will confuse you. Conversely, if you go slightly above mutual information, then even though these code words are generated independently, some of them may actually feel like they are the true cause of the given output. Okay? So using this type of result, we can show that for fixed x2 and y, the threshold for x1 to be confusable is mutual information between x and y given x2, right? And we can have the same bound for confusing x2 with the received output and the true x1. And the sum rate bound comes from just purely random x1 and x2 can be confusable as a true cause for y. So that's why you have this type of pentagonal region. Any question on this? So now, here we have chosen a specific distribution on x1 and x2. We can have many different distributions on x1 and x2. And take the union over all distributions and take the convex hull. And how do you justify the convex hull? If you have one operating point here, operating rate pair here, and another operating rate pair here, then we can simply use a time sharing between different coding schemes to achieve any points that lies on the line segment connecting these two rate pairs. So that means that if you have any achievable rate, then its convex hull is also achievable. Okay? So that way, we go over all pentagons and take the convex hull, then that certainly gives us an achievable rate. Meaning, any rate pair strictly inside this region, we should be able to find a good code that gives us reliable communication. And turns out this is actually the best we can do for multiple access channel, shown by Alswede and Liao in early 70s. So for multiple access channel, now we have characterized the capacity region, okay? And the coding scheme here, even though it is just probabilistic method, kind of hints us what are the good codes. If you use good point-to-point codes, then that'll actually give us nice, reliable communication code for multiple access channels. And this result has been extended to many senders, okay, multiple antennas, even asynchronous communication systems. Now let's move on to broadcast communication system, which is kind of dual to multiple access. So here there is a single sender communicating to multiple receivers, and the channel is also flipped. The sender is using the input signal X, and the receivers are separately receiving Y1 and Y2, and we are sending two independent messages, M1 and M2, among which M1 is intended for receiver 1 and M2 is intended for receiver 2. And as before, we are using the stochastic channel with input x, output y1, y2, n times. So the code, which is just this encoder box, these two decoder boxes, can be defined exactly same as before. Again, we can define the performance of code as probability beta, average probability beta, which is the probability that the intended messages are different from the decoded messages. Okay, and achievability of rate pair is defined as before. We say R1 and R2 are achievable if there exists a sequence of codes such that the probability beta is going to 0, right? And finally, the optimal trade-off between different user rates can be captured by the notion of capacity region. So if a rate pair R1, R2 is inside the capacity region, then that means there exists some sequence of codes with vanishing probability beta. Or said differently, if you give me any target error probability, say 10 to the minus 3, then by making the block size long enough, we can actually achieve the target error probability. Conversely, if you are talking about rate pair R1 and R2 outside the capacity region, right, then there is no coding scheme whatsoever can have arbitrarily small probability beta. Even though the problem is slightly modified, okay, going from many to one to many, the problem actually is open, and we don't know how to characterize a capacity region in any computable form, even for one sender, two receiver broadcast channel. Naturally, there have been many results trying to come up with good coding schemes which are optimal under certain circumstances, and also there have been studies on the outer bound on the capacity region. And here is the most basic coding scheme going back to Cover in early 70s, which is called superposition coding. So when you have multiple messages to send, okay, to different receivers, what could be the easiest coding scheme? Right? For example, I have to talk to Jasper and friends at the same time. Then the easiest way is I first talk to Jasper and then I talk to friends. I can do this type of time division. Right? And this is certainly used everywhere. Here I divide up my time, but if I can somehow talk in two different frequencies, I can split the frequencies into two pieces, and then again I can talk to them, okay, over different frequencies. This is how it's being done in LTE systems these days. Okay? If you think about OFDMA, we certainly decompose the time frequency degrees of freedom into orthogonal parts, okay? And we are allocating different subcarriers to different users. Okay? So that's how we are communicating. Superposition coding tries to do something differently. Okay? In superposition coding, we actually would like to use different times and different frequencies altogether. Instead, we are splitting the space of signals. Okay? So we think of our input x as superimposed version of two different signals, say U1 and U2. And for simplicity, you can view it as there is a U1 signal, there is U2 signal, and you simply add them to generate xn, right? And then you transmit that xn signal, and y1 and y2 each have noisy versions of this x signal, okay? And y1 would like to recover u1, and y2 would like to recover u2. That is superposition coding. Cover used to say that good lecturers actually have some message to all different levels of students. Okay? So you cannot really have a lecture for people of different levels. Somehow you have to convey messages for many different people in the audience who know a lot, okay, or who are just beginners. It's a similar idea. Okay, so now if you look at how we are doing the superposition coding, we are doing the symbol by symbol mapping of our virtual inputs U1 and U2, and that generates X. And then there is our channel. So end to end, you can think of it as the inputs, the channel with inputs U1 and U2 and outputs Y1 and Y2. Okay? And for each receiver, you can view this U1 and U2 as one desired signal and one interfering signal. And the way we do the mapping is U1 is carrying M1 signal, M1 message, and U2 is carrying message M2. So the way we generate these code words is exactly same as in the case of multiple access channel. We simply fix the distribution for U1 and distribution for U2 to separate independent random coding, right? And then Y1 can recover U1 and Y2 can recover U2. So using the same idea as I explained here, okay, and thanks for asking this, Gerhard. So now this should be clear. The rate 1, okay, for user 1 is upper bounded by the mutual information between U1 and Y1. Okay, remember Y1 would like to recover U1. Okay, so there is only one true cause for a given Y1 and everything else is generated independently. So as long as rate is less than mutual information between U1 and Y1, okay, then Y1 receiver can recover the desired code word correctly. And same for receiver 2, as long as R2 is less than the mutual information between U2 and Y2, okay, we have, again, reliable communication for the second code word.
I don't understand. Why? Well, before you had X1Y given X2, here you don't have U1Y1 given U2. So why, before you didn't know the X and receiver, so why don't we have, like if you went to the previous picture.
Okay.
Right. Go back.
It depends on the way we do the error analysis, okay? So in the multiple access channel.
Maybe you can repeat the question because it may
Yes,
be
yes.
terrible in the back.
The question is, before I had a nice pentagonal region, and the question is, why do I have only rectangular region here, okay?
Well, and the expression is different. If you go back to that slide, you will see it's X, Y given X. Here you only have U, Y.
Yes, so let me explain that again. So for the multiple access channel case, it really depends on the specific decoding we are performing. So there, in the multiple access channel case, I was looking for M1 and M2 that are jointly typical with Y. Okay? So here, all the time, I have to handle errors of two kinds. The first error is the true code words I send must be jointly typical with Y. Okay? Otherwise, I have the false negative. I have the true code words, but they are actually not clicked as the true codes. Okay? And that error is usually handled very easily because everything is IID and nice. Okay? So by law of large numbers, true code words are usually jointly typical with Y. Okay? And now, for the case of wrong messages are jointly typical with Y, here I have to decompose the error events into three different types. Okay? So the first type is the true code word for X1 and false code word for X2, and the received output is jointly typical. And the second type is the false X1 and true X2 and Y are jointly typical. Okay. And the third type is false X1 and false X2 are jointly typical with the output. Okay.
That were the 3 lines.
Yes. So the first one, X1 is true, Y is true. I mean, this is what we received. So they are drawn jointly together, and then there is a wrong x1. So that explains the I of x2, y given x1. And the other line is explained by this error event. And the third one captures the sum rate bound. Okay? The sum rate R1 plus R2 is less than I of x1, x2 given y. Now, for the broadcast channel, there are many different options of doing the decoding. But here I'm using a very simple one. Okay? So at receiver 1, I simply do the following decoding. Yeah. Okay, so let me just say this in word. Okay, so there is a U1 code word, right? And then receive signal Y1, and I simply look for U1 code word that is jointly typical with Y. Okay, so in this case, again, we have to figure out whether the U1, the true U1, is jointly typical with Y1, and that can be handled, fairly easily by law of large numbers. And for the wrong U1s, which are generated independently, okay, how many code words I can pack in so that still that error probability is going to 0. The R1 less than mutual information between U1, Y1 gives you the correct bound, okay, as we analyze it here. Okay, and of course, this is not the only way we can do the decoding. Okay, there can be actually more sophisticated decoding. Okay, for example, Y1 can actually try to recover both M1 and M2, and sometimes that is quite useful, especially if Y1 has better decoding capability than Y2. Okay, suppose Y1 gets less noise and Y2 gets a lot of noise, okay, then whatever Y2 can recover, Y1 must be able to recover. And in that case, it's much more natural for Y1 to recover both. So here I'm doing some suboptimal decoding, and we can even analyze how the optimal decoding performs for this case. Okay, but this is a very simple way of doing the decoding, and this rectangular region is certainly achievable for whatever distribution we choose on U1 and U2, and whatever this box, superimposing box, we can put on X. Okay, so this certainly gives us a nice region, okay, of achievable ray pairs, R1 and R2. But the question arises whether we can do better than this, okay? And I told you how to do better. We can perhaps, use better decoder. And again, what is the best decoder? The best decoder is ML decoder, okay? So once you fix your encoding structure, then the best thing you can get is ML decoder, and we can analyze the ML decoder performance. But turns out that is not good enough. How can you do better? Can you somehow make the code words we are transmitting dependent? Okay. Remember, previously U1 was carrying M1 and U2 was carrying M2. And since the messages are independent, okay, it seems very difficult that we somehow coordinate between different code words. Okay. But turns out actually there is a way of doing it, and it goes back to Katalin-Marton. So here is a result by Marton. The region she can achieve looks very, very similar to what we had before. R1 less than the mutual information between U1, Y1, and R2 less than mutual information between U2, Y2. But there is additional bound, which says R1 plus R2 is less than the first mutual information plus second mutual information minus the mutual information between U1 and U2. And at first sight, it seems that we are actually getting less because we have additional constraint. Okay? But the trick here is now we have the choice over not only product distribution on U1 and U2, but we can actually choose arbitrary joint distribution between U1 and U2. In particular, if you choose U1 and U2 independent, the mutual information between U1 and U2 becomes 0, and the third inequality becomes inactive. So we go back to what we had before. So the trick here is, even when dealing with independent messages, how can we actually coordinate these code words so that we make them look as if they are drawn jointly? And this is one of the most beautiful ideas in network information theory, which we call multi-coding. Okay? And certainly it goes back to Martin, but even further back to Kuznetsov and Sivakov in old Soviet. And they looked at the problem to solve how to reliably, how to design memory systems more reliably. Okay? So, unlike most communication problems for which we are assigning a single code word to a single message, here we attach multiple code words to a single message. Okay, so let's see how it's done. For each message M, J, we not only generate a single code word, okay, but we generate multiple code words, okay, which is indexed by L, right? So instead of generating 2 to the NR code words, we actually over-generate many code words and assign 2 to the N delta many of them to each message. And we do it for M1 and we do it for M2. And once again, instead of generating a single code word per message, we are generating exponentially many code words. And you can see why we have additional rate loss, because the receiver will have to decode more. The receiver will have to do more work because we have a lot more code words. What you gain by this exercise is, since there are many code words, okay, we may be able to find good pair that look as if they are drawn jointly. Okay? So that is the pre-coding idea. We over-generated the code words, and since there are many of them, we can always find a good pair that satisfy the desired property. Okay? So for each message M1 and M2, for example, message 1 and message 2, we find a pair that is jointly typical. And if we have sufficiently many code words attached to M1 and M2, then we can find the jointly typical code words with very high probability. Okay? So that's how we do it. So look at all the code words, and for each box with high probability, if we can find a pair that is jointly typical, then to send a specific message, say M1 and M2, okay, we can find a jointly typical pair. Right? So we pick one corresponding to our desired message M1 and desired message M2. We send those code words, okay, and receiver later will try to recover which code word is sent, okay, and once you can pinpoint your code word, we can also pinpoint which slot the code word belongs to, okay. So that way we can have reliable communication and at the same time generate code words that look jointly typical. So this is the idea of multi-coding, okay, and this certainly works pretty well for broadcast channels. Okay, so this coding scheme turns out to be essentially the best for all 2 receiver broadcast channels, and I say it is best known because it achieves the best known performance, okay, but at the same time this is really the best known scheme for broadcast channel. And you probably heard its commercial name called dirty paper coding, okay, and this coding scheme is optimal when the channel doesn't have any noise, or MIMO broadcast channel, or even single antenna broadcast channel, and so on.
What do you say essentially? When I see that, I always think you're cheating a little bit.
Yeah, I'm cheating a little bit, okay, because here I'm using only 2 layers for broadcasting, okay, and what we can do is we can actually use 3 layers. So at the bottom layer, the code word is recovered at both receivers. Okay? And on top, I can use the coding scheme I explained here. And that one is actually achieving the best known performance.
Isn't that superposition coding?
It's not superposition coding because on top, so at the bottom from the bottom to this U1, U2 code word, I'm using the typical superposition coding. But for this U1 and U2, it's not quite superposition coding because they are generated independently, and I still have to entangle them through this type of multi-coding.
Oh, so it has something to do with quantum then?
It's not quantum, it's classical entanglement. Okay.
Oh, there's such a
Yeah. Yes, yeah. So this pre-coding idea has been quite nice, okay, even though it hasn't really penetrated too much to practical coding techniques. But it certainly has applications for coding for flash memories, for example, and there things like this can be used much, much better. Okay? And in fact, people have a very simple, say, short block length codes, okay, to combat the write once memory properties. So write once memory goes like this. You have a memory which can store either 0 or 1, okay, right? But once you write 1, then the memory is stuck at 1, okay? So how can you actually use this memory multiple times, right? And in this case, again, people use the multi-coding idea to reuse the memory for which the part of the memory system, memory cells, is stuck at 1. Right? So that is the same idea as this one. Okay, so how am I doing with time? Oh, it's 10. Okay, yeah, that's good. All right, so do you have any question for basic single hop communication systems? And Gerard is making me realize that how much I'm just skipping, in terms of details. And I'm kind of assuming you already saw some of this and try to kind of introduce the language I'm using. Okay? But if you haven't seen, basic multiple access or broadcast channels before, just feel free to interrupt me. Okay? I'm told that I can go over time later, right? And that just means we are not having lunch, but I'm very happy with that too. So, yes, question.
This strong converse is only for point-to-point or for up to the max?
So when it comes to multi-user communication problems, okay, a lot of things require very subtle definitions. Okay, so for point-to-point, many things are the same. Okay, so you can define the probability of error as average probability of error or maximal probability of error, okay, which means that you want to have reliable communication for every single message, okay, right? And depending on the situations, you can have the strong converse for a certain setting, but you don't have strong converse. Strong converse means that if you go above the capacity or capacity region, then your probability of error is going to 1, okay? Yeah, block error probability is going to 1, okay? Right, so that is what people call strong converse, okay, compared to the converse I talk about, which is called weak converse, which simply means that if you are above capacity or capacity region, then probability of error is not going to 0. Okay, so that is a difference. So whether we have a sharp, phase transition or not, okay, and depending on the situation, okay, we may have strong converse or not, and for single user channels, it is fairly easy. And for these channels, for example, for multiple access channel, again, we have those strong converse, okay, for the average probability of error. But when it comes to the maximal probability of error, it turns out that we actually don't even know the capacity region in general. Okay, so the problem is much more subtle. And for broadcast channel, again, we don't know the capacity region. So we are not even at the stage of talking about strong versus weak converse. So many basic problems are open here. Okay? For example, for multiple access channel, we don't know how to find the capacity region for maximal probability of error. And that's certainly an interesting mathematical problem. I'm not sure really about, practical significance, right? But as a math problem, it's an interesting problem. For broadcast channel, okay, again, as a math problem, it's very interesting to figure out what the capacity region is. And many smart people worked on the problem without, really solving the problem, okay? But for many practical scenarios, the capacity region is known, okay? For example, for all binary input, the broadcast channels where one receiver or both receivers are binary symmetric channel and then the other is binary erasure channel. For that scenario, the capacity region is known by work by Chandra Nair. Okay. For Gaussian broadcast channels, again, the capacity region is known for both single antenna and multiple antennas. Okay. So several practically motivated channel models, we know the capacity region, but the capacity region in general is not known, even if you limit your attention to binary input broadcast channels. Even binary input, binary output broadcast channels. So a lot is not known. Any other question? Okay, so we'll move on to the relay channel, which is the simplest model for multi-hop communication, multi-hop cooperative communication. So here we have a single sender and single receiver, and they would like to communicate a message M, okay, by sending X1 and receiving Y3. So you can view this as node 1 and node 3. And what is node 2? Node 2 can both receive something from the channel and then re-encode it into X2. Okay? And this node is called relay, whose sole purpose is to help communication between node 1 and node 3. So here we want to send one of 2 to the NR messages over N uses of the channel. So the rate of communication is R. Okay? And encoder is simply mapping the message M into its code word X1N. And decoder would like to decode Y3, the noise observation Y3N, Y31 up to Y3N, and to recover a message M. And the burden is on this relay box, which causally observes Y2 sequence, and based on that, it generates some new signal, X2. So at time I, the input at relay, X2I, is a mapping, is a function of all the past received Y2 symbols, Y21, Y22, up to Y2I minus 1. As before, we defined the average probability of error as the probability that the uniformly distributed M is different from the message estimate M hat. Okay? And achievability of a single rate is defined similarly. We say the rate is achievable if asymptotically we can achieve reliable communication, and capacity is the largest achievable rate. So as before, below capacity, we have a good code that achieves arbitrarily high reliable communication. Above capacity, there is no reliable coding scheme whatsoever. And the problem of finding the capacity is not known in general, okay, even though it is a very simple point-to-point communication with one additional node. And naturally, the literature is full of a lot of relaying schemes. Okay? So the problem really became how we design this box. How do we design this relay? So there are very basic coding schemes. Okay? You probably heard about this. Decode forward, amplify forward, compress forward. Okay? And then you add some adjective like partial decode forward, non-coherent decode forward, coherent compress forward, generalize amplify forward. Okay? And then there are a few other ones, hash forward, compute forward, quantize map forward, rematch forward, and so on. And then there are things that don't have forward, but still they are doing the same forward. Okay? So network coding, analog network coding. Okay? And then there are local dialects. Calculate forward, clean forward, combine forward, demodulate forward, denoise forward, detect forward, estimate forward, flip forward, mix forward, quantize forward, rotate forward, scale forward, select forward, sum forward, truncate forward. So at this level, we really feel that our society, the community, is very good at following Steve Jobs' advice. We are merging technology and the liberal arts, okay? Right? And I'm not really joking about these 4 schemes. Okay? Whenever you find a good verb which has been used by somebody else, then you have a nice paper written just by choosing the right verb. Okay? So if you go to my website, I actually collected all these 4 schemes, and if you click it, you'll find papers written on specific forward. Okay? But jokes aside, okay, I mean, some of them must be quite useful, and many of them are actually extensions of the basic coding schemes, right? And the most basic coding schemes are decode forward and compress forward. And before discussing them, I'm going to actually introduce some performance benchmark for all these forward coding schemes, and which is called the concept bound. Okay, so Kovar and Elgaval in 79 wrote a classic paper on relay channels. So we are going to look at many results from that paper. And one result there is the capacity is upper bounded by so-called cut-set rate, which can be written as the maximum of minimum mutual information between x1, x2, y3, and x1, y2, y3 given x2. Okay? So here is a mnemonic for understanding this bound. Okay? And the first bound is cooperative MAC bound. So the capacity or the information flow should be upper bounded by the amount of information x1 and x2 can cooperatively send to y3. Okay, and another bound is this is amount of information x1 can communicate while y2 and y3 are cooperating to recover the message. Okay, and I'd like to say this is just a mnemonic. I mean, it just helps you interpret the result, but the actual result, I mean, there is no cooperation, of course. This is just serves as a way of interpreting the bound. Okay? And we, of course, have to first take the minimum of these mutual information terms and then maximize over all possible distributions. Right? So this is so-called cut-set bound, okay? And we are going to use this bound as performance benchmark for other coding schemes we introduced along the way. Okay? And to get to the decode forward, I'm going to gradually build a coding scheme. So what is the most basic way of using the relay? Well, that is not using the relay, which is direct transmission. So for direct transmission, relay doesn't do anything. So it simply sends the most favorable signal. Okay? And for the typical communication, you can think of it as just relay is being silent. Right? And then now from node 1 to node 3 communication, it's exactly same as point-to-point communication. And for point-to-point communication, we know what is the best. We can choose the maximum mutual information by carefully choosing our input distribution on x1 and maximize the mutual information between x1 and y3 under the relay being silent. Okay? So this is what we can achieve. The other extreme is not using the direct link, okay, but simply use the relay. So every communication is done through relay in a multi-hop manner. Okay? And here, the basic idea is the following. We are going to think of communication as being over B blocks. So there are B blocks total. And over that B blocks, we are going to send B-1 messages, pipelined one at a time. Okay? So over B blocks, we are going to send B-1 messages indexed as M1, M2, M3, and so on, up to MB-1. So at block 1, the sender transmits M1, block 2, sender transmits M2, and so on. And for the relay, in time block 2, it sends M1, it relays M1. In time block 3, it relays M2. And in time block B, it relays MB minus 1. So that is so-called block Markov coding, which is just network information theoretic jargon for pipelining or multi-hopping. Okay, so again, this is how it goes. In block J, node 1 transmits MJ, right? And at the same time, node 2 transmits MJ minus 1. The message in one step before, okay? And by end of the block, relay can recover MJ, which will be transmitted in the next block, and node 3, the receiver, recovers the previous block's message. Okay, so this is how we do the coding. And following the similar argument, okay, the relay can recover the new message X1 is sending if the rate for MJ is less than I X1 Y2 given X2. Okay, remember X1 is the signal we want to recover. Okay, Y2 is my received output and X2 is what I already know. So I can achieve this much at the relay. And final destination node would like to recover X2 by treating everything else as noise. So the previous block's message MJ minus 1 is recoverable if that rate is less than I X2 Y3. So as long as the message rate, which is assumed to be the same over all messages, is less than the minimum, okay, then we have reliable communication, and we have the freedom to choose arbitrary distributions for X1 and X2, so we can take the maximum. So this much is achievable. So this is a very simple multi-hop communication coding scheme. Now, here is one step we can do better than multi-hop, which is what we call coherent multi-hop. And the idea is the following. Whenever I'm sending something, I'm sender, I already know what to expect from the relay, right? Because relay, if everything is working fine, should be sending what I just sent a minute ago, okay? So the sender has complete prediction of what relay is gonna do, and my operation can piggyback on what relay is supposed to be doing, okay? So instead of using two independent code books, okay, what X1 can do is, based on what X2 is sending, we can cooperatively transmit what X2 is sending as well as some fresh information. So I can always superimpose my signal on top of what the relay is transmitting. Okay? So by using the simple superposition coding, X1 can send both previous message and current message, and by doing so, we can actually use code words that are jointly distributed. Okay? So this way, we can get so-called coherent multi-hop, and everything is the same as before, except that now we can increase the set of distributions as the joint distribution. So this is coherent multi-hop, and the idea is, again, very, very simple. Because the relay is decoding the message, the sender can predict what relay is doing, and therefore, we can design our code words to be compatible with what the relay is sending. And finally, this is the last improvement we can have on this type of coding scheme. And previous two coding schemes were completely ignoring the signal that is going directly from X1 to Y3. When Y3 was recovering the message, it was simply trying to recover what X2 is sending and try to ignore the signal from X1 as interference. It was considered as noise, even though it contains what I want to recover in the next time slot. Okay? Remember, in block J, Y3 would like to recover X2, which is carrying MJ minus 1. And at the same time, X1 is sending fresh message. Okay? And the way we are doing the decoding, this Y3 was ignoring what X1 is sending, even though she will need it 1 block later. Okay? And that is a complete waste of what we could have done. Okay, so here is a way of recovering the signal from both X2 and X1. And there are many different ways of doing it. And the one I'm presenting here is so-called backward decoding. So here is how it goes. At each time, X1 is sending new message based on the previous message. Okay, so that is how we do the transmission. The relay recovers the messages one by one and try to transmit it, forward it in the next block. So everything here so far has been same as the multi-hop coding scheme. How can Y3 decode better? Here is so-called backward decoding. Yes.
Who invented backward decoding?
Backward decoding goes back to Franz Willems and Ed van der Meulen. Okay, but this particular paper was not written by them, but there was another group, okay, who picked up the idea and applied it to the relay. Okay, so I was about to say that later. Yeah, yes, yeah. But it's okay. Yeah, the order doesn't really matter because we are gonna do the best decoding here anyway.
Where did Franz first publish that?
Or was it the Benelux Information Theory meeting? Was it? Wasn't? Uh-huh. Yeah. 82, yeah. Anyway, so here is the idea. Okay. The receiver doesn't try to decode at a time, but wait until the end of communication. Okay. And now we look at it here. At the end, now we see that both X1 and X2 are actually trying to send the MB-1, and that is the only remaining uncertainty in what X1 is transmitting and what X2 is transmitting. Because at block B, X1 has exhausted all the messages he had to send, so it is only helping the relay communicating MB-1. Okay? So now, it's very easy to recover a single message out of two signals, X1 and X2. I mean, you can even view it as, say, distributed MIMO. Okay? There is a single message, and M1 and X1 and X2 are trying to cooperatively send the same message. So we can recover it. And then go backwards. And now we look at the signal X1 and X2. We already know MB-1. So again, the uncertainty is on MB-2, which is transmitted cooperatively by X1 and X2. So we recover MB-2. So we just keep going on backwards. And at each stage, we actually have to deal with a single message, which we treated as interference, okay, before for the signal coming from X1. Okay? So this way, every stage, there is a single uncertainty and how much information transfer we can have from both X1 and X2 to Y3. We can have I of X1, X2, Y3. So this is the idea of decode forward. Okay? And this particular coding scheme we use is backward decoding, which goes back to Franz and Ed. Okay? And there are many other coding schemes which in effect achieves the same region. Okay? The original coding scheme by Kovar and Elgamal uses the binning, the random binning at the relay and list decoding at the receiver, which is not very easy to implement. Okay? And later, this idea was made more streamlined by using forward decoding instead of backward decoding, using something called sliding window coding. Okay? And that work is Xie and Kumar, and also Gerard and Michael Gaspar, and who's the?
It was actually Carlisle's paper implicitly already.
Yes, yeah. Carlisle did it for the Mac with generalized feedback, which actually includes even relay channel, but it was made popular by the later groups in 2005. Okay, Jay and Kumar and Gupta, Gaspar, and Kramer. And they managed to extend it to larger networks because of that simplification. So using this decode forward coding scheme, now we can actually recover this additional symbol x1 in the achievable rate. And it's very easy to compare it to the cassette bound. Okay, so now this bound, the cooperative MAC bound, is completely achieved by decode forward. The trouble is with this bound. In the cassette bound, we have the cooperative BC, which is I of x1 and the receivers. And in decode forward, the single relay should actually recover the message. So we have only I of x1, y2 given x2. Okay? And even though it's a single term, the difference can be actually significant. So when the relay is close to the sender, so relay can decode much, much better than the receiver, then this term doesn't affect the performance very much. But when relay is getting a weak signal, this coding scheme can be actually even much worse than direct transmission. Okay? Because we are overburdening the relay. So relay really becomes a performance bottleneck for this scheme to be successful. So there are two solutions. One is so-called partial decode forward, which you are going to see in a minute. Okay? And in this case, we recover only part of the message. We don't ask the relay to recover everything. Relay just recover only part of the message, and forwards that part it could recover, and the rest is just going directly. And another coding scheme which we call compressed forward. And in this case, we actually don't do any digital operation, digital decoding operation at the relay. Relay simply treats its received signal as analog signal, performs vector quantization, and send the quantization index to the receiver. So probably this is a good time to have a short break then. So after break, let me talk more about these two improvements on decode forward. Okay, welcome back. So I hope I'm not skipping too much of the basic material, and I appreciate Gerard's questions because, you know, I mean, on one hand, I really want to go to very recent results. I mean, up to say last year, okay. But on the other hand, I mean, to understand that, we have to understand the basic ideas, you know, basic random coding, multiple access channel, and broadcast channel. And I sort of assume that 90% of you have already seen some of these materials, but I mean, it's good to be reminded of, you know, what's going on at the very basic level. And for 10% of you who haven't seen this, you know, whenever there is something that is unclear, just please let me know, okay? I'll try to explain, you know, even though, I mean, you can see, you know, this is kind of, you know, nighttime in California, so I'm a little bit, you know, shaky, okay, in explanation and so on, but I'll try my best to explain the basic things so we can build up nice story on top of it. Okay, so I'll continue our discussion of the relay channel, and we talked about decode forward, okay, and it was a pretty good scheme. You know, we could completely piggyback on what relay does, and the receiver could extract full information from both X1 and X2, but the trouble is we are overusing the relay. We are asking the relay to recover the entire message, okay, so the performance bottleneck is really at the relay, and therefore it could be even worse than the, you know, direct transmission when the relay is, I mean, really bad. I mean, relay's reception is really bad, but still we are forcing the relay to recover the whole message, and we are hoping some magic to happen. And the magic seldom happens. So this is one improvement of decode forward, which we call partial decode forward, okay? And in information theory, okay, I mean, there are many ways of, you know, doing better than the usual transmission, okay? Say, I talked about time division versus superposition coding before. So time division, you know, if, you know, there are two competing, you know, objectives, we just divide up our time and just, you know, serve two different purposes, okay? But information theory tells us actually there is a better way of doing it. We can perhaps just decompose the signal space and try to use two different signals. And that's what is happening here. Okay, so here we decompose our message into two pieces. So every time the fresh information is decomposed into M prime and M double prime, right? And the relay just takes care of the prime part and try to forward the prime message, okay? And the double prime message is not recovered at the relay, but still the receiver would like to recover that. So that is the idea of partial decode forward. And how do we implement this? We implement this using superposition coding. So the relay part is exactly the same. Relay is using X2 code word to forward the prime message, okay? And at the sender, I actually use the virtual message U, which plays a role of X1 previously. Okay, so previously, X1 was sending fresh message on top of the old message. And instead of using X1 signal, now I'm using U signal to send the prime message piggybacking on old prime message. And on top of it, I'm going to superimpose a new signal which carries the fresh information based on whatever the rest of the message. Okay, so saying it again, I'm just using decode forward for prime message, okay, with input U and X2 and output Y2 and Y3. So up to this part, it is exactly same as decode forward, except that I'm not using X1, I'm using U. And then I'm overlaying transmission of double prime message just as in direct transmission. So that is how we do achieve the performance of both direct transmission as well as decode forward. Okay? And as you can expect, because we are using them superimposed in the signal space, that means that there could be some synergy. We might be able to do the better of the better.
Does this work for a wired network?
How do you model the wired? So these links are all separate. Oh yes, yeah. For wired network, actually, this is something far better. Okay. Yes. So the official question here was.
There it works. Okay. The official question was: does this work for if this was a wired network? So if you had a wire going from X1 to Y2 and X2 to Y3, and then a third wire going from X1 to Y3, what does this mean?
So for the wired network, actually, this is a very good example where direct transmission utilizes only this link. Decode forward utilizes only, yes, direct transmission utilizes only, decode forward utilizes only this link, right? Okay. And if you use partial decode forward, then you actually get the sum of the minimum rate of this path and this one. Okay, so for example, if this is 1 bit, this is 1 bit, and this is 1 bit, then partial decode forward will achieve 2 bits. Okay, per transmission, decode forward will achieve only 1 bit, and direct transmission achieve only 1 bit.
It's like flow. So it's like
yes,
flow.
Yeah, it's like flow. Okay, so I'm decomposing my information flow into two subflows, and I'm using decode forward for one flow and direct transmission for the another. Okay, so this is what we can achieve. I mean, I'm not going to go through the exact derivation, but the basic idea is basically what we want to do is we achieve certain rate using U and X2 to decode forward rate, and on top of it, we can send additional information using direct transmission. So this expression I write, which we'll revisit sometime later, okay, when we are not using any U, okay, then that means that I'm not using any direct transmission, any decode forward. Okay, so in this case, what we recover is direct transmission. Okay, and if we use only U and X1 is not doing anything on top of U, then we recover decode forward. And of course, as that wired network example shows, we can actually do better than we can actually achieve more than the better of the two. And here is another way of writing the same rate region, the same rate expression. Okay, and this expression is kind of hinted in the paper by Elgamal and RF, right? And if I write it this manner, then it's much easier to compare with the cut-set bound. Okay, so for cut-set bound, I have this cooperative MAC mutual information. Okay, and instead of I of x1, u, y3, x2, y2, y3, x2, in place of y2, I have u, and then there is additional penalty term. Okay, so this is one way of rewriting the partial decode forward rate. Compressed forward is operating at a completely different philosophy. Up till now, okay, the relay was doing digital to digital interface. So there is some digital signal coming in, and the relay wanted to recover that digital information and then do another digital communication to forward what the relay has recovered. For compressed forward, we have, in some sense, analog to digital interface. So the relay is treating the received signal as some analog source. We want to do compression of it, or vector quantization to be more precise, and then send the quantization index over the channel so the final destination can use both its received signal as well as the quantized version of the relay signal to recover the message. Okay? So the quantization part can be viewed as analog because we are not trying to extract any digital information from relay's output, but the quantization index should be communicated using some digital communication. Okay, so we have to encode the quantization index using X2 coder, then communicate. So that's why I call this as analog to digital interface. So here the codebook is just X1 carrying the message at each block, and X2 is carrying the quantization index of the received output, and this one, the Y2 hat, is the codebook to be used for quantization of Y2 signal. Okay, so here is how it works. The encoding is fairly easy. It's simple. Every time we send a message M1 up to time B minus 1, okay, and at the end of each block, Y2 try to recover the right quantization, okay, and then instead of sending the quantization index itself, one version of compressed forward actually sends the hashed version of the quantization index, okay, and then in the next block, X2 is sending the hash of the quantization index, and finally, the final destination recovers the hash of the quantization index, and based on that, it actually recovers the quantized code word. And based on that and its own received signal, it recovers the message and move on and on. Okay? So this is so-called compressed forward scheme. And you can see this one looks, conceptually more complicated, okay, because it involves hashing, quantization, and so on. Okay? So in some sense, this one actually didn't get a lot of attention. Okay? Even during the days of Kober and Elgamal. So Elgamal actually didn't expect this result to be quite useful and optimal in some cases. That is from his channel lecture. But turns out this one also is very useful, as we will see later. So Slepian-Wolf hashing is a little bit different in a sense that in Slepian-Wolf, the objects that are being hashed are not uniformly distributed. But here, what we are hashing is essentially uniformly distributed. Okay? So here we can have so-called structured hashing. So what you can do is you have the codebook of quantized indices, then you can simply just partition it in a very structured manner. For example, if your quantization index has, say, 100 bits, then we are only sending the first 50 bits. Okay? So that suffices here. So this is what we can achieve using the scheme I very briefly described. Okay? So we can achieve any rate mutual information between x1 and quantized version of y2 and the received signal y3. But there is some constraint on the distribution we can choose because we have to guarantee that y3 has no problem recovering y2 hat. So the mutual information between x2, y3 should be greater than the rate we need for quantization, okay? Which is given as I of y2, y3 hat given x2, y3. The detail here is not very important. The basic idea is very simple. We quantize the y2 signal, somehow communicate it to the final destination, and final destination utilizes both its own signal and the quantized version. Here is another way of writing the same rate that can be achieved, and this probably appeared first time in 2006 by Al-Gamal group, the Mohseni and Zahedi. Okay. So here they can actually maximize without any constraint, but now we have an expression that resembles the Coset bound much better. Okay. So here is Coset bound for comparison. So the second term, the broadcast bound, is essentially the same except that instead of using y2, the true y2, here we use a quantized version. And here now the MAC bound, we lose something because we have to communicate y2 signal to the final destination. So this is a comparison between partial decode forward, compressed forward, and the Coset bound. So this is our Coset bound, right? The MAC bound and the broadcast bound. Okay. And for the case of partial decode forward, the MAC bound was as before. The broadcast bound now had U instead of Y2, and there was some penalty term. And for compressed forward bound, the BC bound is essentially the same except that here I use Y2 hat. And for the MAC bound, I have some penalty. Okay. So even though these two coding schemes are completely different, I mean, both philosophically and the way they operate, actually their final results look, essentially very similar, in some sense dual to each other. Okay. And writing everything in this form also tells you what would be a good way of choosing our, say, U codebook, for example, or Y2 codebook here. Okay. So we can demonstrate how to do that using the Gaussian relay channel. So here everything is Gaussian. X1 is broadcast to both Y2 and Y3, and Y3 receives the signal from both X1 and X2. So here we have the broadcast channel. At the same time, we have multiple access channel here. Every noise here is Gaussian, okay, and the channel gains, signal from 1 to 2, okay, 2 to 3, and 1 to 3 capture everything you want to know about this channel. And this is a very difficult channel to deal with because for any case where the channel gains are non-zero, we don't know the capacity. So this is a difficult problem. But we know how to approximate the capacity fairly well. So here is a known result. Okay. The difference between the Coset bound and partial decode forward is less than half. Okay. So that means that partial decode forward can achieve within 1/2 bit from the capacity, even from the Coset bound. So that means Coset bound is tight within 1/2, partial decode forward is tight within 1/2, and we can conclude the same thing for the Coset bound. And this result has been known for a while, and you can see the MIMO extension of the result by some paper written by Jin and Kim. Okay. And by looking at this expression, it tells us how to choose U. The way we should choose U is U should be chosen in the exact same form as Y2, okay, except that it is conditionally independent to Y2 given X1. Okay, so here Y2 is generated from X through Gaussian channel, and we simply take another independent Gaussian channel to generate U. Okay, then we can see this one will be exactly same as this. Okay, and this term, the negative term, has very small effect because we are talking about two independent looks of X1, one at Y2 and another at U. Okay, and they should be, about the same. Okay, so this term will be very, very small. for compressed forward, it also tells us how to choose y2. Okay, so if we choose y2 too close to, y2 hat too close to y2, which means that our quantization is too fine, okay, then of course this term will be very, very close to this one, but the cost of quantization will be very, very high. At the same time, if you quantize too coarsely, then this one will be small, negligible. The cost of quantization will be small, but this term will not catch up very well with the broadcast cut. So the right balance was found by Avest, Meyer, Digavi, and Tse. Okay, so we simply just quantize y2 at the level where noise power is same as the quantization noise power. So the channel noise has the same statistical behavior as the quantization noise. Then we are losing a little bit here and a little bit here, but not very much when you look at both terms. Okay? So by these choices, we can easily check that the gap between the cassette and partial decode forward and compressed forward is bounded by 1/2 per transmission. So here is how it performs. I mean, by varying different values of the channel gains, we can see that the cassette bound is here, and say here, compressed forward is closer to the cassette bound than partial decode forward. Okay, but all of them are within 1/2. Okay, if we move the relay closer to the encoder, then decoding is actually a better strategy. So partial decode forward is very close to the cassette bound, and compressed forward is worse, but still they are all within 1/2. Okay, so for a single relay, I mean, these results are fine, and we know how to combine both compressed forward with partial decode forward. So that is the most complicated result in Kobayashi paper. And for that one, we actually don't know exactly how close we can make the performance to the cassette bound. Okay? There hasn't been any analytic study of how to reduce the gap, but I mean, I'm pretty sure for all practical purposes, it'll make the gap much smaller than 1/2. Okay, so any question so far? Right, so we've been talking about very simple relay network with simply 3 nodes, sender, one destination, and 1 relay. And now we are going to talk about something far more complicated with a lot of nodes. So when we talk about relaying for networks, we first think about what are the basic tools we have. Okay, and network information theory, I mean, there are only a handful of basic tools. One is simultaneous decoding, okay, which sometimes used to do the multi-user sequence detection at the receivers. Okay. Superposition coding, we saw multi-coding, Blanc-Markov coding, decode forward, compress forward. I mean, these are basic tools we have. And what we are really missing is some building instructions so we can put these basic coding techniques together so we can generalize our coding scheme for the relay network with many nodes. Okay? And we are going to go over 2 building instructions called noisy network coding and distributed decode forward. Okay? And just before we go into the details of these schemes, okay, we have to realize that often the vanilla extensions don't work. Okay? For example, if we just want to use the partial decode forward as is to the network, then it becomes very difficult. Okay? Because in partial decode forward, what did we do? We decompose the message into 2 pieces. Okay? And relay was decoding 1 piece, and the other piece was transmitted directly. And now suppose that there are many relays. Okay? And then do we have to really decompose the messages into many different pieces? Okay? Say there are 2 relays, then there should be a piece that is recovered by relay 1, there should be another piece that is recovered only by relay 2, and there should be a piece that is recovered by both relays, and there should be another piece that should be transmitted directly. So that is only for a single message, and now suppose there are many messages. Then who decodes what, and I decode this part from this one, and so on. I mean, it becomes out of control. Okay? So we actually have to do a little more than just basic extension, okay? And at the same time, the building blocks should be refined. I mean, here is the same opera house, but if you use crude pieces, then you can go only this much. If you use finer pieces, then you can actually get something that looks much, much better. Okay, so with that in mind, we are gonna go over two different network communication scenarios, and the first one is so-called multiple access relay network. So in this scenario, there is a final destination node, a single common destination node in the network. There are many different senders trying to communicate to the common receiver with the help of a bunch of relays. Okay? And here I drew it with a bunch of lines, but it doesn't necessarily mean that signal travels only this way. I mean, here, any receiver can hear, any input from anywhere. Okay? So the basic model is basically we look at the outputs y1 up to yn as a stochastic output of a bunch of inputs x1 and xn, and the network has n nodes, and each node has input xj and output yj, right? And some of the nodes have messages, okay, m1, m2, and so on, and one of the nodes, say n, wishes to recover all the messages, okay? So this is a very simple model for multi-hop uplink communication, right? And in the so-called Cloud RAN architecture, people usually look at the two-layer structure. So there is the bottom layer where there are a bunch of handsets, and then there is a layer of many base stations, and then there is the final layer where the centralized processor have access to all the base stations and try to do the combined decoding. Okay? But here we look at something more general. So here each box at the nodes can be modeled as this. Every node here, I mean, I assume that everybody is sender, okay? So everybody except the node n is a sender, so they want to send some messages with rates r1 up to rn minus 1, okay? And everyone is encoding its own message as well as whatever it has received so far. So everyone is sender, but at the same time serving as relay for everybody else. Okay? And then decoder would like to decode its noise observation yn to recover all the rest of the messages. So this is the general model of operations here. And of course, we are interested in finding the capacity region or having some close approximation of it. And we also like to find, more importantly, we would like to find the coding scheme that achieves capacity region or a decent approximation. And the benchmark we are going to use is cassette bound, okay, going back to El-Gamal in 81. So here we define a cut of the network as partition by partition of nodes S and S complement, okay, right? And we define the rate for the cut as all the rates of nodes on the S side going to the S complement side. Okay, so here I look at the messages on S side, so look at their sum rate, and they are all to be decoded at destination node N. So I define the sum rate as Rs, and the cassette bound states that for every cut, okay, that separates the final destination from any of the messages, the sum rate must be upper bounded by mutual information between inputs on S side to the outputs on S complement side, given inputs on the S complement side. And we have the freedom to choose any arbitrary joint distribution between x1 up to xn. So this is the El-Gamal's cassette bound, which gives us non-trivial trade-off between the rates R1 up to Rn minus 1. And of course, this one is not tight. Okay, we have very simple examples where this is not tight. Okay, but we'll use this as our benchmark. And the coding scheme, one coding scheme that achieves close to the cassette bound is so-called noise network coding. And you can view this as using compressed forward for the networks. So here, one version of noisy network coding, the operation is fairly easy. At each node, we would like to quantize its noise observation. Okay. So here again, we are using analog to digital interface at every relay. So every relay is taking the quantization of its out signal, the received signal, and then next block, we send this quantization index along with the message we would like to transmit, and just keep going on. And the final destination node would like to recover all the messages as well as the quantization indices from every relay. And this coding scheme turns out to perform relatively well. Okay, so the basic ideas are mostly what you have seen before. We are going to use block Markov coding. Okay, so we are going to split the messages over B blocks of n transmissions, just as in the regular relay. And relay is doing compress and forward. Okay, so relay K observes YK, and we want to find the good quantized code word for the received signal, and we want to transmit it. In the next block, relay transmits its own message along with the quantization index, right? And the final destination recovers all the messages and all the quantization indices. Yes. So there are many different ways of doing it, but one version we are talking about here doesn't actually does the hashing, okay? Right? And you may wonder why we needed hashing in compressed forward, okay, before. And actually it turns out for the compressed forward, again, we can do it without hashing, okay? But the analysis is a little bit, difficult, as well as this analysis. Okay, so with hashing we can reduce some redundancy. Okay, but if you think about it, what you really need is the message itself, not the quantization index. Okay, so if your coding scheme really would like to know the quantization index, then you have to code, very carefully. But in the end, the final destination actually doesn't really need any quantization index. All she cares about is the messages. Okay, so hashing or not doesn't really make any critical difference in the end. Okay. So this result was, in a sense, the first recovered by, first established by Yasai and RF. Okay, not known to many people in the community. So I thought I was doing something different. Okay, until lately. So Lim, Kim, Elgamal, and Chung published a paper called Noise Network Coding. And turns out what they were doing was, essentially the same thing with different coding scheme, but achieving the same rate region. Okay. And then later, Ho and Kramer came up with a coding scheme, in some sense, is conceptually much easier to follow. Okay. But they are again achieving the same rate. So I'm not going to explain how this analysis is being done. There are many papers written. Okay, you can either read Ho and Kramer's paper. Okay, Yasai and RF is very difficult to understand, so I wouldn't recommend it. Or you can read Lim, Kim, Elgamal, Chung, or read Elgamal and Kim Network Information Theory book. Then there is some analysis there, relatively accessible. Okay, but the rate we can achieve is the following. Okay. And I'm going to compare this with coset bound, pretty soon. So here again, the sum rate across some cut S is upper bounded by mutual information between X on S, Y hat on Y, S complement, okay, minus there is some penalty term which captures the cost of quantization, how to transfer the quantization index from the relays to the final destination. Okay. So this bound can be specialized to networks with specific structure, and one network which became quite popular after work with Abestmeyer Digavitse is deterministic network. So this is a network where every output is just a function of the inputs. So the channel doesn't have any noise, okay? But it still captures the effect of broadcast as well as interference, and it can be a good proxy for the Gaussian network when the signal-to-noise ratio is very, very high. Okay? But at the same time, interference-noise ratio is also very, very high. Okay? So for this case, the Cossette bound simplifies, which is given by this mutual information as conditional entropy of y as complement given x as complement, because given x at S and x at S complement, we have inputs throughout the network. So the second mutual information term becomes 0. Okay. So the Cossette bound becomes this simple conditional entropy term over all cuts, over all joint distributions. For the noise network coding, we can again take y hat as same as just non-quantized version. Okay. And here, the quantization actually doesn't cost anything here because I can condition on xn. So if I take y as y hat, the first term becomes exactly same as before and the second term becomes 0. So I get the same conditional entropy, except that here I have to take the product distribution instead of the joint distribution. So as long as the network has a special structure, okay, some sort of symmetry over its alphabets, okay, then the optimization over joint distribution will be same as optimization over product distribution, and therefore we have established the capacity region. Right? And that's tied for graphical networks, okay, which models the wireline networks. So every node to the node link is orthogonal to each other. Okay? Or the network doesn't have any interference, then still we don't have to take any joint distribution. The product distribution suffices. So for these two examples, okay, we have established the capacity region. And of course, all these results, these are not new results. The capacity region for graphical networks is exactly same as the famous network coding theorem by Alswede, Tsai, Lee, and Young. Okay, and the deterministic network without interference is done by Gerhard Kramer. And who was the other student? Ratnaker, who was interning at Bell Labs. Yes. Mm-hmm. Yeah. So this result is due to Ratnaker and Kramer, and Ratnaker was student of Ralph Gotter doing the internship at Bell Labs. For the Gaussian network, where received signal is the superposition of input signals, okay, appropriately attenuated by the channel gain plus Gaussian noise. The Cossette bound, again, can be written this way, and noise network coding bound can be written this way. And from our exercise for compressed forward earlier, we know exactly how to take the quantization. So the quantization noise should be at the same level as channel noise. And this goes back to Abestmeyer Digabitse. So if we use this one, okay, and do careful analysis, then we can actually show that the gap between the Cossette bound and what it can be achieved by noise network coding is 0.63 n, where n is number of nodes. Okay? And this holds uniformly over all possible channel gains and the power constraints. And on one hand, this is a decent result because we have a uniform bound regardless of the channel parameters. So this is so-called constant gap approximation of the capacity region. On the other hand, this is not super exciting because your gap increases linearly as the number of nodes increases in the network. And subsequently, there have been many topology-dependent improvements of this bound. Okay? For example, if you have two-hop network, then you can reduce this bound, okay, when there are n relays from order of n to order of log n. Okay? So you are losing only by order of log n if you have very simple two-hop network, which is probably useful quite a lot in the Cloud RAN architecture. So now let's go back to the dual problem of broadcast relay network. Okay, so here there is a single server who would like to control a bunch of relays to talk to many different receivers. And as before, we model it by general network with outputs y1 up to yn, with inputs x1 up to xn, and each node each node j has control of input xj and output yj. And node 1, say, would like to send messages, independent messages, to be broadcast to a bunch of different nodes. Okay? So here we'd like to broadcast independent messages over the relay network. So this is a simple model for multi-hop downlink communication. Okay? And we can define the code. Similarly, here the encoder has access to all the messages and its own channel observation. The relay encoders are causally encoding its noise observation into its own input signal. And after n transmissions and uses of this channel, every relay, every node from 2 to n would like to recover its desired message based on its channel observation. Okay, and again, we'd like to ask what the capacity region is, okay, and what is the optimal coding scheme or close to optimal coding scheme that achieves capacity region or that can go close to capacity region. So for this case, we have a dual expression for capacity region. Okay, so here we'd like to again decompose the network into two pieces, S part, which contains node 1, and S complement part, which doesn't contain node 1. Okay? And we'd like to look at the sum rate for the receiver zone S complement side, and it is again upper bounded by mutual information between input zone S and output zone S complement over all possible input distributions. So that is our performance benchmark. And for this one, now we are going to use partial decode forward and try to extend this to the network. And the way we do it is so-called distributed decode forward. So I alluded earlier that if you really want to explicitly decompose the messages into small pieces and decide which relay decodes which part, it becomes out of control. It is a very, very difficult problem, and it has been attempted a long time ago by RF. So he had a simple relay model, and he could actually explicitly decompose the messages. But it was a very simple 2-hop relay network, and it's quite difficult and for single message. But now here you have many, many messages, okay, and many relays without any layer structure. So it's unclear how we are going to actually achieve that goal. The way of doing it is by introducing virtual code words, as in Martin's coding scheme. Okay, so we are going to introduce a bunch of new code words, one per relay, say U2 up to UN, and we are going to introduce their indices L1, L2 up to Ln. Okay, and what we are going to do is, since encoder has every messages and it can do the encoding for the entire network because there is a single encoder, what we do is we are going to generate these U code words, over-generate them. So all the code words as well as what we are sending, okay, as inputs are entangled together. So here, as in Martin coding, we are going to do the pre-coding at the single sender node, and single sender node does the control of all the signals that will be propagated through the network. So that is a basic idea. Okay. So as before, we are going to use the block Markov coding. Okay. We are going to decompose the message into small pieces. Okay. And here we'd like to guarantee that all the code words we are transmitting are jointly typical. And to achieve that, we use so-called backward encoding, which is very similar to the backward decoding we showed before, but we actually gonna do it in the encoding manner. So we are gonna do something similar to Martin coding for all these blocks, starting from the last one and then propagate backwards. Okay, so that is what we call backward encoding, right? So after this stage, okay, what we can guarantee is all these U code words, which are virtual code words, and all the X code words, what we are going to transmit over the network, are jointly typical from block 1 to block B. For all blocks, whatever we are transmitting are jointly typical. And the relay's job is fairly easy. Okay. Relay, by looking at YK, recover its virtual code word index, right? And at the next block, we simply transmit XK, carrying this LK signal. So here, by doing this encoding stage, we are actually implicitly decoding some information about the message without explicitly partitioning the message. Okay? So that is the key idea here. So these auxiliary code words are not really shown to have any components of the messages we are transmitting. But since we are forcing them to be jointly typical, they are implicitly carrying some information about the messages, and that information is actually carried, recovered at each of the relays. So here is some more detail. Okay. So here is a codebook structure. The relays are always trying to send the index L, okay, one per relay. And there are U code words, okay, that are carrying some information about the message, okay, as well as indexed by virtual index L, right? And X1 code word is conditioned on everything over the entire network. And here we use the fact that, fully use the fact that relays are decoding the messages. Therefore, we know exactly what relay is doing at any given point of time at any place in the network. Okay, so we explicitly use that. So that's how we can send X1 signal that is completely conditioned on everything else. Okay, so we are going to do the backward encoding. Given messages, we would like to find all these L indexes. Okay, and once you find these L indexes, now we can transmit X1 signal as given here. And at each time, the relay is sending XK signal, okay? And then at the end of each block, relay would like to recover its desired signal as well as the pseudo index L, which helps communication of other relays, other receivers. And then in the next block, we transmit that L index and keep going on. Okay? So this is, again, doing the decoding at the relay because we are finding some digital index at relay. But that index is related to part of the messages in a very implicit manner, which is guaranteed by pre-coding stage at the sender. So when you specialize this one to the simple relay channel, we actually recover the partial decode forward result. So this is the achievable rate we can get from this distributed decode forward scheme. You can see the similarity of the cassette bound as well as partial decode forward before. There is a cassette-like term except that instead of Y, we have U, okay, and then there is additional penalty term, which is capturing the cost of doing the pre-coding or entanglement. For the determinist case, this was actually studied by Kanan Raja and Vishwanath in 2012. Okay, so the cassette bound becomes like this, distributed decode forward bound becomes like this. Okay, so here we have the familiar conditional entropy term as the sum rate bound for all joint distribution. And here by taking U as same as Y, and this is possible because the channel is deterministic. Okay, and then we have just product form of input distribution of the same conditional entropy. So whenever the network has a special structure as before, just like the graphical network or network with no interference, these bounds are all tight. And for the Gaussian channel, we can do the same thing as before, starting with coset bound, okay, and distribute decode forward bound. We know how to choose U from our earlier exercise for partial decode forward for relay channel. Okay, so we choose U, which looks very similar to Y, except that they are conditionally independent. Okay, then we have a complete control over this term, okay, and we have a very good control over this term. And we can show that the gap between the coset bound to what we can achieve is 0.5 n, when n is the number of nodes, regardless of the channel parameters for Gaussian networks. Okay, and this term again, the half n, can be reduced to log n when we have a certain structure in the network. So, for example, for 2-hop network, we can make it log n, and we can even make it up to half log n. So here is a summary of distributed decode forward and noise network coding. The DDF is used for broadcast relay network, and this one is for multiple access relay network. So they are in some sense dual in terms of traffic pattern. Okay. For distributed decode forward, the decoder structure is relatively simple. Okay. It's the encoder which have a complete control over the entire network. She knows everybody is doing what at each given time, okay? And all the burden is at the encoding stage. For noise network coding, the encoder and the relay were simple. It was the decoder who had to recover all the messages as well as some of the compression indexes. When you simplify everything into single hop, distributed decode forward simplifies to Martin's inner bound, which I showed you earlier. Okay. And noise network coding simplifies to the multiple access channel capacity region. So it at least passed the test whether these are reasonably good when everything is single hop. When you specialize to the 3-node relay channel, okay, distributed decode forward becomes partial decode forward, okay, and noise network coding becomes compressed forward. And the gap for the Gaussian is 0.5 and 0.63. And you may wonder what will happen if the traffic is intersection of broadcast and multiple access, which is just a unicast from a single source to single destination. Okay. Then these coding schemes are all doing fine. Okay. We can recover all these results. And even for multicast network with single source and multiple destinations recovering the same message, we recover the standard network coding theorem. Okay. So this one can be viewed as the noisy version or noise network extension of network coding theorem. So any questions so far? Okay, so now even though we don't know the general capacity for general network, we have a decent theory for multiple access and broadcast. Okay, and probably these two flow patterns are good enough for cellular networks because we have a more controlled network with a single, central base station or central processor, okay, dealing with all the, reception as well as all the transmission. But in reality, if you think about a broader class of relay networks, the harder problem is actually multiple unicast. Okay, so here we have many transmitters, trying to communicate to its own destination. For example, this guy is using YouTube, and here is a YouTube server. Okay, this guy is using Vimeo, and here is Vimeo server, and this guy is using Evernote, and here is Evernote server. And these companies are not really friendly to each other. Okay, so there is no centralized processor. So we'd like to do the communication utilizing all the relays in the network. So this is so-called multiple unicast problem, which is very, very difficult. I don't know how to do the coding for this network, but at least what I'm going to show you now is how to upper bound the capacity, okay, which is better than improving the traditional cut-set bound. Okay. So for this case, again, what is a capacity region? The capacity region is, here we have a sample network with 7 nodes, and here these arrows all mean the flow. So it doesn't mean the network topology, it simply means the network flow. So node 1 has some message to node 4, node 4 has some message to node 7, and so on. Okay? So there are 1, 2, 3, 4, 5, 6, 7 different flows in the network, color-coded, okay? And we'd like to characterize or bound the capacity region, which is, as usual, the closure of the set of achievable rate tuples. Okay, so that is the question we have. The cut-set bound, okay, going back to El-Gamal and made very popular by Cover and Thomas in their network information theory chapter, goes like this. We partition the network into 2 pieces, okay, S and S complement. We look at the sum rate of all the flows with sources on S side and destinations on S complement side. Okay. Then that sum rate must be upper bounded by mutual information between XS and YS complement, okay, for arbitrary joint distribution between all the inputs. So this is the classical cut-set bound. Okay. So here we have the freedom to choose different cuts, and that's how we are making the bound tight, okay, depending on the flow pattern. So we go over all possible cuts, and then we take the union over all input distributions. So it has the max-min feature, okay, which is in general tighter than minimax. Okay, and the minimax bound is actually, the minimax cut-set bound actually goes back to Ed van der Meulen's old paper. His early paper on relay channel actually does the minimax bound. He first compute the capacity for all different cuts and then take the minimum. Okay. But the improvement by El-Gamal Cover was they did a minimum first and then did a maximum over the input distribution. Okay. So anyway, this is the general cut-set bound. Okay. So for example here, if we take this cut, then this flow, this flow, this flow are separated by S and S complement. And how about this one, 3 to 5? Well, it doesn't count because we always start from S side as a source and S complement side as destination. Okay? So we have 3 flows, and the mutual information is all the inputs on this side, 1, 2, 5, 6, and all the outputs on this side, 3, 4, 7, 8, conditioned on all the inputs here. So that's how we generate a single inequality, and then we go over another cut. Okay, so here we have this flow, this flow, this flow. Okay, so their sum rate must be bounded by inputs here, outputs here, conditional inputs here. Okay, and we go over all possible cuts, all meaningful cuts, which has some source on left and some source on right. Okay, and then we generate bunch of mutual informations. So that'll give us a polymatroidal bound on the rates. Okay, and then we take the union over all joint distributions. So that gives you the cut-set bound. Okay, so far so good. And now let me try to introduce some concept which could be new to several of you, which is the notion of directed information. Okay, so here I'm going to denote by A1 up to AN and B1 up to BN as a pair of sequence of random variables. Okay, and I'm going to attach the meaning of time for these indices. Okay, so that A1 and B1 are kind of viewed as, clocked in the same time. Okay, and A2 and B2 are clocked the same time, and so on. Okay, even though I'm not going to use any temporal connotation later in my talk. Okay, so if you look at the mutual information between A sequence and B sequence, then by the chain rule, the mutual information can be represented as mutual information between the whole A vector and Bj given Bj minus 1. So this is how we expand the mutual information. Graphically, each term in the sum is mutual information between all A, and each B. Okay? Conditioned on the previous B's. The color is not working really well, but anyway, I mean, here I'm conditioning these guys. Okay? Directed information is slightly different. Okay? It is typically written as directed information from A sequence to B sequence, right? And instead of looking at mutual information for the entire A vector, I use the A vector up to current time and look at the mutual information with B at that time, given past B's. So this is directed information, and this notion goes back to Markov, okay? Even in the late 60s, early 60s, okay? So he studied this in the context of cybernetics, but his most famous paper in this regard is his 73 paper, okay, which was published in IEEE Transactions in Cybernetics or Communications, yes, yeah, Communications, okay, yes, Communications, where he actually studied the amount of causal influence in the group of monkeys, okay. So there were a bunch of monkeys, one of them was a leader and there were subordinates, okay, and he quantized their actions into many different ones, I mean, attacking, eating, and so on, and he wanted to figure out the information flow from either subordinate to the leader or leader to the subordinate, okay? And so he wanted to figure out whose action is influencing whose action more, okay? So what is your guess? I mean, there is a subordinate and, and there is a leader, okay? For example, France is a leader and I'm subordinate, so I'm doing some action and he'll some action and vice versa, okay? So whose action will influence who's more? The subordinate to leader or leader to subordinate? Okay, I mean, if monkeys are good citizens like us, then probably that is the case. Okay, but turns out actually it's the other way around. Subordinates is doing some action, and then leader reacts upon it. Go beat him. Okay, right? So that's how their actions are causally influencing. Okay, so that's Markov's theory back in 60s and 70s. Okay, and Massey picked it up, okay, when he was trying to understand the effect of feedback in communication problems. So he coined the term directed information as opposed to mutual information, which is symmetric between A sequence and B sequence. I mean, here now we have broken symmetry between A sequence and B sequence, and he actually used this to characterize the capacity, feedback capacity. I mean, didn't quite characterize. He found a very nice upper bound on the feedback capacity, which has been proven to be actually the capacity by many people, including Gerhard Kramer's earlier work, okay, and several other papers on feedback communication. Okay, so one interpretation we were able to get later in the work with Permuter and others is Permuter, Weissman, and myself, is this directed information from A sequence to B sequence has a very nice interpretation, okay, which is somewhat orthogonal to the usual interpretation in communication, and it goes like this. Okay. This directed information can be interpreted as the amount of information A sequence provides about B sequence in a causal manner. Okay. So again, here, usually we can think of this as the input and this as the output, but it's the other way around. Okay. There is some random sequence Bn, right? And you observe An sequence, and you want to learn something about B sequence. How much you can learn about A based on B, but you are learning only causally. Okay. So this is the interpretation of directed information. And please keep this in mind when we see more complicated expressions in the next few slides. Again, it's the amount we are learning about B causally based on A. Okay? And here is so-called directed Coset outer bound on the capacity. So let me first state the bound. This is work with Sudeep Kamath and myself. Okay? So here, instead of bipartiding the graph, the network, we are gonna partition the network into multiple pieces, okay, right? And we look at all the, and we are gonna, assign the numbers for these subsets. So we always go from this side, say this is V0 and V1 and V2. So here we tripartite the network, okay, and we look at all the rates, okay, that is going from V's on the higher floor to lower floor. Okay, so we look at all the traffic, the flow from V1 to V0, V2 to V0, and V2 to V1. Okay, so you can think of it as, a tall building, and everything, information can only fall down from top to bottom. Okay, so we look at all the rates. Okay, and this sum rate for correctly aligned information flows is upper bounded by directed information from the output sequences, okay, in each floor, okay, to input sequences in each floor condition on the bottom input, okay. So what is the interpretation, okay? What was the interpretation of directed information? It was the information you learn about the input based on output in a causal manner, okay. So for this particular example, we look at the information we learn from output here about inputs here, okay, and as well as the amount of information we learn about this one based on this, and so on. Okay, so that is the interpretation of this directed concept bound. Here is an example. How many flows are flowing from top to bottom? I mean, here is 1, 2, 3, 4, 5, 6, right? So some are going from flow 1 to 0, some are going from 2 to 1 and 2 to 0. Okay? So we look at all the sum rate. Okay? Then we look at directed information from this output, okay, to this input and this input. Okay? So this is the mutual information, the amount of information output here can learn about this one, okay, right? And output here can learn about this one. Okay? So that is the amount of information you learn as you go up the building, step by step, floor by floor, causally. Okay? So that is the interpretation of this bound. So here, actually, there is the causality here has nothing to do with time. Okay? Here, we are simply using the analogy of causality just for spatial decomposition of the. No, actually, non-causal is still fine. It's just that it is too loose. Okay? Just go back to the mutual information and directed information. Here, directed information doesn't actually use the entire sequence, so therefore this is smaller, assuming the joint distribution is the same. So by doing this, you actually get a much tighter bound. Okay? So here is the difference between the standard concept bound and this directed concept. And as you expect, I mean, this one I'm just making a cutlet out of the network. So here I have much finer partition. Okay? So here the sum rate, cut by this partition is upper bounded by directed information. But for the usual concept bound, we just do the bipartition. Okay? We bipartite the network, and therefore, if you look at the directed information for bipartition, then that just simply can be written as mutual information, and that is exactly the same bound as Elgamau's, the traditional concept bound. Okay? So the traditional concept bound can be viewed as a special case when we limit ourselves into only, partition of two components, and the way we improve over the standard concept bound using directed concept bound is introducing more and more cuts. And how many more is needed? It can be shown that you don't need to do more cuts than the number of messages, okay, right? And in fact, if there is a single destination node collecting all the messages, or a single source node broadcasting all the messages, then this bound, the directed cut set bound, simply collapses to the standard cut set bound. You don't really gain anything by introducing more cuts. So I'm going to illustrate the point by this 3-node channel, which looks exactly same as our relay channel, but it's not relay, in a sense that node 1 is communicating some message to node 2, and node 2 is communicating some message to node 3. So this is not relay channel, right? And for this not relay channel, here is the typical way of doing the cut set bound. I first make this, the light blue as a source cut, S, and this is S complement, okay? Then I get the rate upper bound for this one, because this is only cut one, right? So this is S, and this is S complement, and R12 is upper bounded by this mutual information. By taking this as my source part, this as my S complement, I get this bound, okay? And any other cut you generate is actually looser than what we have here. So with a standard cut set bound, we get only these two inequalities per joint distribution. Now, with a cut left bound, okay, directed cut set bound, I can have this cut. Okay, so this is a source. No, sorry. So with this one, what I can do is, yes, I can do, I probably colored it wrong. Okay, so yes. Here I have now tripartite the network. So 1 is on its own, 2 is on its own, and 3 is on its own. So the information flow we can cut through this partition is 2 to 3 as well as 1 to 2. Okay? So the sum rate is bounded by mutual information, directed information for 0 level y, which is y3, the first level y, which is y2, 2, the first level x, which is x2, and second level x, which is x1. Okay? So I mean, it's confusing because the node indices are reversed, but again, this is the lowest floor and this is highest floor, and we are looking for information flow top to bottom. Okay? And this directed information, okay, which Gerhard toiled throughout his PhD work, and he simplified, a lot of things using new notation and so on, simplifies into sum of mutual informations in this manner, okay? And this bound is not implied by any of these two, and in fact, by introducing this new bound, we can get the right degrees of freedom, okay, when we simply look at the Gaussian relay network, while this one is pretty loose. Okay? So this one gives us a non-trivial improvement on the cut set bound, and most likely this one, if we know how to find the matching coding scheme, this one will be the right bound to look for multiple unicast networks. Okay, so let me summarize what we've been doing so far, and hope I didn't really eat up too much of your lunchtime. Okay, yeah. Sorry for the 15 minutes loss. Okay, so we've been talking about a bunch of building blocks for wireless relay networks. Oh, okay, 12:30. Oh, okay, so I have time. Yes, yeah, that's great. Yes, yeah, thank you. I thought we are done at 12. And we also talked about some building instructions. And for multiple access relaying, we have noise network coding, okay, and broadcast relaying, we have distributed decode forward. So where are we really going? Okay, what's really missing is we have a bunch of components here, okay, and this is School of Information Theory, so probably it's okay to be useless, and usually communication theorists and information theorists are competing who's more useless, and usually information theorists win the game fairly easily, okay? But what are you gonna do with this? I mean, are you gonna write papers, books, okay, and get promoted and so on? I mean, is that our goal? Or do we really want to make some impact in reality? I think to really make some impact, we have to build practical codes implementing all these ideas we talked about here. I mean, there are many good results, we have produced so far, but I'm sure there is a lot more to be done. Okay? So really, the key point here is all these little Lego pieces, we have to make them into practical pieces. Okay? And some part of practical codes will be discussed, I think Thursday, right? By Tim Brink. So he'll go over the historical perspective as well as the current frontier of coding theory, including spatial coupled codes and polar codes. And one thing you can keep in mind is how these codes can be really implemented, used to implement some of the ideas we talked about today. Actually, not much has been done, okay, along this venue. On the instruction side, okay, it seems that we have a decent, not perfect, but decent building instructions for two kinds of flows. One is multiple access flow, and the other is broadcast flow. But the general elephant, big elephant in the room is the multiple unicast flow. Okay. So for that, I think directed concept bound can be the one step in the right direction. Okay, so we have now improvement, the general improvement over the concept bound. What is really to be done, okay, is how we are gonna do the coding for multiple unicast. And for unicast coding, the multiple unicast coding, the problem is very, very difficult. Even if you remove noise in the network, if you just look at the graphical network, the network modeled by graph with noiseless links, the wireline network, even there, we don't know how to solve multiple unicast, even for two unicast problem. Okay, so I'm sure tomorrow, Michael Langberg will talk a little bit about network coding, index coding, and these type of problems. And there, the key point is how to solve the multiple unicast over the network, which I believe is one of the most important theoretical as well as practical challenges in network information theory. Okay, so here are some references I used. Okay, I didn't put all the references. This is a very egocentric list of citations. Okay, and at least one Kim's in the paper are all me. Okay, right. And talking about ego. Okay, so do you know this person? Okay, so he's very famous in Zandvoort, I believe, okay, but even Dutch people don't know him. Okay, so his name is Igor Leonard, okay, and he actually floated from the ocean in 2007 and somehow came to the beach of Zandvoort. Okay, and turns out, every year he was showing up in many different beaches, once in Bristol and then Florida, and recently even in Japan. Okay, so. And this is exactly the same beach, we are gonna go walk outside later. Okay, so with that, let me conclude my talk. Thank you.